Hey everybody, Dave Lindbergh in Hong Kong with another episode of THD Podcast. Today, joining us from Silicon Valley, we're going to have Michael Ricci from xMEMS to tell us about his Piezo MEMS speaker technology. So we're very interested to find out more about that. But without delay, let's make sure we give a shout out to our sponsor, Alti, the Audio Loudspeaker Technologies International. Always a mouthful, but always a good time. So make sure you check them out. They're a great networking resource. I know they're looking forward to get back to their automotive show coming up sometime this summer. But anyways, once again, please check out Alti as a good resource to network in the audio community. So without delay, let's say hello to Simon in Japan. Hello, Simon. How are you?
Very good. Morning, Dave. Evening, Michael, I guess.
All right.
Down there.
Hello.
So
Good evening.
Michael Ricci, thank you for joining us today. Appreciate your time. Heard a lot about xMEMS, so maybe you can tell us a bit about how long the company's been around, and then let's get right into the technical explanation of what you guys do and what's hot about it.
Sure. The company's about almost 4 years old. 2018, I believe, was incorporation and basically operated in stealth mode while developing a Piezo MEMS transduction mechanism. And that's been applied to micro speakers. And now we came out last year with some new products that are entered the market, and they're made on a silicon wafer. So this is an 8-inch wafer from our fab partner, and it has a ton of our identical speakers. Every speaker on here is identical. And so kind of interesting because it's all monolithic, manufactured in a semiconductor wafer process.
How many speakers are on that wafer, roughly?
I don't have the number a lot.
Is it like 100? I mean, it's not quite clear. Is it like 100 or is it 10?
I would be guessing. I can start counting, but we're going to run out of time.
Okay, but we'll put the number we'll super the number after we get it after this after we have this interview. We can count it later. Maybe
the number shouldn't be shared.
Oh, okay.
Let's not get me fired already, guys. We're only 5 minutes in.
Okay. All right. So how do you want to tell us about how it works? Do you have a presentation to walk us through, or?
Yeah, I think I could. I have some renderings that I think might help explain the new transduction motor, how it's put together. And then we can get into that. And then that same slide deck was really put together to help people test these, because now that they're out in the marketplace, as far as evaluations and prototyping goes, most of the likely suspects have our devices. And so I've been kind of the customer-facing engineer, helping them evaluate and test the speakers. So I had to put together a deck to help them test it. And I felt, well, I better start with what is the device under test that we're working with, and how is it different? Because there's some unique attributes and behaviors of the Piezo MEMS that are different from a voice-coil based dynamics or balanced armatures. So that's just something that I thought is a good place to start. So I think we should do the same here.
Okay, let's get into it then.
Great. So thanks for the opportunity, gentlemen, to let me present this to your audience. I think it's pretty interesting. I thought I knew what it was when I was being interviewed here, but then after opening the hood and looking underneath and working with it, there's definitely some cool stuff going on here. So we call it Piezo MEMS, based on the piezo material is doing most of the work in the system, deflecting and moving the radiating surface, which is fabricated with the MEMS process. And it's applied to micro speakers specifically for occluded designs now, but we're also working on higher output devices for leaky ANC and TWS designs.
Okay.
So what you see here is kind of a rendering, what would be a kind of a crude definition of what we have, which is a silicon substrate. Then there's some metallization, and then we're applying a thin film piezo material, which gets charged with the amplifier. And then there's some additional over metallization that happens. And then we also kind of do something to the membrane to make sure it has independent suspension. So there's some bypass for the moving structures. And so we're able to actuate this with voltage from a Class H amplifier. and it behaves really interesting. It has a very high resonant peak, up somewhere north of 16 kilohertz, closer to probably 18, and becomes more efficient in the high frequencies with the equivalent input, which I'll show in the frequency response plots that I've got prepared. But some of the other interesting things about using a MEMS manufacturing process is all of the devices are near identical. So wafer to wafer, lot to lot, the sensitivity, the frequency response, the behavior of the speakers are nearly identical. There's maybe we test to in the data sheet to under this number, but we print in the data sheet 1.5 dB, but we're holding under a dB in final test. And we test them in an anechoic chamber in an automated system.
So that must be incredibly valuable for people building ANC type devices where you're having to tune each system once the speaker's in place based on the frequency response. Is that correct?
There is a lot of sorting that goes on in the dynamic driver space and in the BA space where people want to match up transducers. Mm-hmm. So you get phase coherency. And then you can imagine, when you're working with multiple transducers in a two-way design with a dynamic and a BA, or maybe a dynamic and two BAs or multiple BAs, like some of the intermonitor companies use, you want to make sure your drivers are as close in sensitivity and phase as you can. And so, yes, this does help a lot. We've got people experimenting with our speaker and some of the fastest MEMS microphones that are available, because we're trying to match a low mechanical response or fast mechanical response with low group delay. So, that's exactly what's going on in the background. Several companies are actually experimenting with what they can do with giving back some latency budget to the algorithm engineers in tuning the ANC system.
So you've got down there low group delay, 100 hertz to 2.5 kilohertz. Could you just say a little bit about that?
Yeah, well, so we tried measuring our mechanical response on a popular transducer measuring system that uses a laser. However, we're so fast that system couldn't resolve the speed. We actually had to shoot it with a polytech laser, which is used in the MEMS transducer space for companies that make inkjet print heads and other types of moving structures that oscillate at high speed, and basically scans the membrane and calculates its displacement. So we had to use that type of a sophisticated instrument on an air-bearing table in like a university lab. And what we were able to find out is that we're 30 to 150 times faster than the DD or dynamic driver that we were using as our control sample. That came out of a popular large company's ANC TWS earbud product that was very expensive. So we thought that was a good candidate speaker to measure. That speaker's mechanical response is in the millisecond domain. Ours are in the microsecond domain. And you might notice on the back side, you did notice the two pads, Simon, but there's a solder ring around the back vents. And I'd like to talk about that for a second, because that's what helps us separate, front volume from back volume. Like a MEMS microphone, you've got a ground seal ring around the bottom port. Well, it's very similar SMT approach here. And so each cell that you see here in gold, underneath each one of those cells is a plurality of holes, right? And so that's how we tune this speaker. We call it a speaker because it's a finished speaker. That's our cabinet. That's basically a ported system, ported in the front and ported in the back, and by design controls its behavior, because we know what an occluded ear canal is going to be for pressure, and we also know what atmosphere is in the back volume of an earbud. So we've equalized the design.
Is there any kind of process for surface mounting these parts to like a quality control or a special paste or something that needs to be used to order to make a good seal at the back? Is that something that you have to dictate?
Just solder. Yeah, just same thing for a MEMS mic. Yeah, just regular SMT reflow standards. Just following best practices you would do for a MEMS mic. Same thing here for the MEMS speaker.
Okay.
Nothing different is required.
Okay.
Yeah.
You would have holes in the board to match the rear vent holes, would you? Or do you put a big, just put a routed cutout in the board?
Well, then there'd be less pressure. So we're trying to control.
So what you're saying is you can actually build it without making holes on your PCB that you're mounting it onto.
If you mount it on the PCB, then those back vents need access to atmosphere at some point in your design. So you just don't want to cover them and block them.
Right.
But as long as there's some way that either through just some space out to the back of your earbud, you would have a small pinhole. Let's see, I think I have one here.
Yep.
I can show, but usually a 0.5 millimeter hole, like on the back side here. Or anywhere really on the product, as long as that's there and you can equalize the internal pressure to the back volume of your product, then no problem. It's going to operate with a 2 dB LFRO all the way down to 20 hertz.
Right.
What's interesting about the membrane is I mentioned before, there's some bypass gaps in it. So here you could see it's an array. It's actually 6 identical cells in the photograph. And each one of those cells is a 20 hertz to 20 kilohertz transducer all on its own in an occluded design. We have 6 of them arrayed together to get the SPL target that we're after. But each one of those cells, you can see, is made up by 4 sections, kind of like 4 trapezoids, if you will. And those actually can move. They don't touch their neighbor. There's a little bit of a slot there, or a slit in the membrane that you could see at like a 45-degree angle. And that kind of gives us, bypass. What I noticed after spending hours listening to these things over the last year and a half is I was able to go 4 hours without having ear fatigue or bass bother my eardrums. And I'm going, wow, this is really crazy. These comply tips are comfortable, but they're not that comfortable. After a few hours, I'm want to pull them off and just let my ear canal relax a little bit. But I wasn't getting inner ear fatigue. I wasn't feeling pressure on my eardrum from listening to music for hours and hours on end and tuning and listening to a lot of bass. And I was trying to contemplate what was going on there. And then after looking at some COMSOL models of how we actually actuate and measure this stuff for finite element analysis, I'm realizing that the DC static pressure that's building up in my ear canal, it only goes up to a certain level and then actually gets evacuated out through the flaps going up and down. So you don't really get a buildup of pressure in your eardrum in a fully sealed system where the transducer doesn't have holes in it or bypass gaps in it. That's trapped air. But we actually can shift some of the air from inside the ear canal to the back volume of the earbud, which is really interesting. It allows for longer listening and less DC static pressure building up in the ear canal. Yeah, and so why silicon? Why would anyone want to use silicon? So this was something that I thought was interesting to share, because if you talk to a speaker designer, they're going to tell you, I want the lightest, stiffest material with a high resonance outside of the critical bands. I want, so they can achieve a fast transient response, and they would love it to be resistant to changes in temperature, moisture, and humidity. And that's exactly what the silicon offers us. Is a pretty ideal material for this type of small speaker. Now, just so there's no confusion on what you're seeing on the dime there, the white is just, we were practicing early on with protective mesh before we realized we were IP58 survivable. And so before we had that rating, we were actually trying out some different mesh and materials to kind of protect the membrane, but we don't ship with that now. It's not required. It has a little bit of a cover tape on it when it ships out to the users, and they just remove that before they go into assembly. And then this gives you a little bit of an idea of the side port versus the top port. So on the right side is the top port, in the center of the package is that opening. And on the left side, I kind of circled it with a little bit of a red dashed line, is the side fire. So that allows you to almost have like a zero footprint. If you put that on the inside wall of your earbud, what did I do with that guy? You'll wind up taking up very, very little space. So let me pop this off. So can you imagine if that's just along this inside edge here, you have the whole rest of your earbud open for allowing a bigger battery or maybe another sensor or two if you're doing some kind of sensor fusion or fitness tracking, and you want to have some other kind of feedback from the device that's inside your ear canal. That's lots of extra room available inside the package when you're using the side fire. It's just over 1 millimeter tall.
Okay.
Yeah. And then, as I was describing earlier about the form factors here, there's a kind of a two-way BA stack with a kind of a woofer BA and a tweeter BA, and then next to it is kind of an average dynamic driver we see in some of the designs. So yeah, it's a little bit different than what we're used to seeing, but this is a standard semiconductor SMT reflowable package, and a lot of companies really want to put this on flex and reflow it on, and flex kind of decouples things from the mechanical structure where you don't have to have it touching the same PCB as some other things. So it helps to mechanically isolate the speaker from the microphone and vice versa when you're using SMT.
Yep.
Okay.
You can also solder wires on. The pads are big enough for manual assembly for wires.
Okay.
Oh, okay.
And then on the bottom is just some renderings of some things that we've worked on. We have to make some EVKs ourselves. EVKs meaning that we have to kind of produce some 3D printed housings and put our speaker inside so people can hear the top port, the side port, and then we got our feet wet with tuning, using dampers in the output tube. Some acoustic impedance dampers you can place in, and it shapes the frequency response. And then you think you got it sounding good, and then the sales guys come back and say, "Hey, we need the Harmon curve," and then you got to go back and change some things around and do some tuning and get the response right and pump the bass and maybe match the Beats curve because they have a little bass boost. And so all of that's been fun to work on, but it kind of forces us as a transducer manufacturer to actually get into a little bit of our hands becoming dirty with a basic design. So really they're just meant for listening, so people can just put them in their ears and kind of hear what the transducer can sound like, the high precision, the clear sound, the accurate reproduction. And that's really what we've done here with an in-ear monitor style design. And also you could see a rendering on the lower right where we have 3 microphones placed in there for say an implementation for putting a TAWS A and C type of an earbud together. And they're just examples, right? We've got probably 10 or 15 of them now of different designs where we can give the customer our CAD and say, hey, here you go, try this design. If you like the way it sounds, follow these geometries, use this damper. Here's the EQ curve. You can duplicate exactly what you heard of the EVK if you want, or you can kind of, get into the DSP and tune it any way you want, really.
Okay.
So that's kind of the device under test, a unique transducer with some interesting behaviors. Here's our test lab. This is what we're using here to verify that the material that we're getting from the packaging partner that goes out for shipping meets and matches all of the data sheet results. So what we do in this lab is we compare our measurements with our engineering facility in Taiwan. So they do the characterization. They're using Gross ear and cheek simulator. They have 711 coupler. They're using listen sound check. I'm doing the same thing here, except for my coupler's B&K. And we recently got, I don't know if you guys can see, we have the 5128 hats or the high frequency head. We finally got ours from B&K with the new 20 kilohertz ear sims. And so we just compare measurements back and forth between the labs. And once that's achieved, I take that test script, I make it available to the customers who are doing the eval measurements, because it's important when you ship a product to a customer that they're able to at least verify datasheet performance. And so I'm making sure everything that goes out matches that. And then I share those test scripts with the companies that are receiving our samples. And then I help talk them through the stimulus, getting the signal set up into the amplifier correctly, and then making sure they're getting the frequency response and the THD measurements that they that match ours, and then they're free to go off into the wild and experiment with their prototyping. So pretty standard equipment, nothing super fancy.
Yep. Super fancy.
Well, I mean, we don't have a full hats. We just have the head, and I didn't even need the head for a while. I was just using the ears. So I think all in, this was a $30,000 a purchase to get us into testing, not 130. So
Right.
but my next budget that I'm asking for maybe a little more. And here's an example of what we're using to test. We're using the standard 711 coupler We're using a free field or a pressure field mic, depending on if we're going to do some baffle or open air measurements, which we have to do from time to time. The speaker is intended for occluded designs, but as you see on the right side here, we put a couple of housings together and experimented with free air. We wanted to see if these can be put in glasses or glasses frames. And pardon me while I lift my laptop up, but I'll back you up and show you. Let me know if you guys can see. I call him Harry because, obviously he doesn't have any, but these are like some glasses. These are kind of prototypes where we're putting the transducers in the frames. And, we're making measurements here and finding out that we can propagate sound in free air in the mid-range and the high frequencies. We can't really move any bass. Obviously, we don't displace that much X-max to, have that much X-max in the system to make bass and free air, obviously. But for the mids and the highs, it's pretty clear and it's pretty loud too. So we actually brought these to CES and we're demoing in our suite, and people were quite surprised at the high frequency resolution and the detail and the sound that they were hearing just out of our prototypes.
It's got a lot of applications as this augmented reality products and virtual reality products become more popular. I think one of the feature sets that people want is, if they're virtual reality, is you can't have your ears occluded as well as your eyes occluded. So the ability to have open air listening, personalized listening devices is a kind of a upcoming market demand, especially in VR applications.
Yeah, no kidding. I was thinking about that because since it's a cell-based kind of approach, you can have an array in an arc around the ear and generate quite a bit of energy in mid-range and high frequency, and maybe work that with a large dynamic and have some kind of spatial effects around the ear.
Yeah, you don't want people lost in the metaverse and not realize the fire alarm's going off.
I think I'm already lost in the metaverse myself, but yeah. So let's see. Basically, yeah, Bluetooth. So we have a Bluetooth module up on the mixer there. So when we pair up and connect, we can also do some testing with the Bluetooth connection here when we're doing some comparison to TWS and other glasses that are Bluetooth oriented. This slide here just shows what comes in an evaluation kit. We have a little amplifier board, which I'll show you here. I prefer to run everything off DC when doing testing because I don't like AC coupling to using like power supplies on laptops or electricity, and some places aren't so clean. So we always ship a DC supply, 3 AAA batteries, and there's a pair of our amplifiers on here. So 2 mono amps. That's what's inside the box. It says xMEMS here on the screen. And basically that just steps up voltage. We take anywhere from 2.5 to 3.3 volt input, and then it multiplies that up. So as I mentioned earlier, the amp's capable of 30 volts peak to peak. That drives us to max SPL. However, listening at a moderate level, you're probably only going to be operating the amplifier between 2 and 4 volts peak to peak. So to get, kind of 85, 94 dB SPL is achieved at 4 volts peak to peak at 1K. So I would imagine that people aren't listening at 94 for a very long period of time. But that's what the amplifier delivers. And so we give the schematic and the reference circuit to the customers so they can lay things out. We actually even recently put the amplifier and the BOM, the whole required peripheral passives, on the back of the side fire substrate. So we were able to make a slot for the bypass gaps on the back vents, and then literally put the amplifier circuit on the back of Montera package. So it's a powered studio monitor for your ear to do some rapid prototyping too, with some big solder pads on it. So that's pretty helpful. A lot of the customers have adopted to try those first, since the amp circuit's already integrated for them. They don't have to lay anything out or order flex or do soldering of Litz wires, which is everyone's favorite thing to do.
What's the supply voltage you need?
Minimum 2.5, but 3.3 supply for it would be what would drive the amplifier to max output.
Oh, okay. Yeah. And it's stepping up. It's stepping up that output voltage.
Yeah.
You mentioned before class H amplifier, was it?
Yeah, it's a class H. We tried class. We started out by using an amplifier that was available in the marketplace that was designed for piezo devices. It was originally a national semiconductor part, and then after TI bought them, they kept the part in production. So people in the space that work with piezo devices know the LM48580 really well. Decent amp, but it's extremely dated. It's over a decade since it probably was designed and first released, and hasn't been optimized since. But it works, right? And it gave us an opportunity to get sample kits out and send these things out to customers on these test coupons. Give them some coupler adapters to screw onto the 711, and they were able to start making some measurements and seeing how the transducer behaves. But the power consumption for that TI amp was high, and the BOM that was required for it had some components that are just a bit too large for a TWS, say, integration. So we experimented with some Class D vendors, but Class D and its switching behavior wasn't a good match for the piezo MEMS structure that we have. So we hired our own team. And we developed our own amplifier based on a Class H design, a standard Class H circuit that we worked with. And they, in under 10 months, released our first amp, which we now have in production and shipping out in evaluation. So that was really cool. We came out with that and have another one on the way with even less power consumption.
What is Class H?
Class H is sort of like a rail follower is kind of the nickname for it. It looks at the input signal and then it provides just enough or just slightly more voltage and current than the input signal requires. So it's not quite a switching design, but it does modulate the output based on what the input signal is asking for. And so it's efficient in its power consumption. It's not just giving max current and max voltage at steady state at all times and letting the transducer figure it out. It's actually tracking what the input signal is asking for, if you will. And then it provides that voltage and current accordingly. And I think there's a small amount of extra for headroom, obviously, in the system to make sure it behaves in a linear fashion.
Okay.
And then let's see, let me grab the coupler real quick because I'm really kind of excited about this thing here. We're using a lot of, compound and stuff to kind of seal things in. And that's when we figured out, well, we should really come out with some way of using a test coupon. And then let's see how we get the test coupon into the coupler. And that took a little bit of design work on our side. So let me open this up real quick here. A little fun with the toys. So we have these coupler adapters for the Gross coupler and also the B&K coupler. And so there's a different thread count and a slightly different size for the outside of those couplers, but they all have the same, I think it's 4cc on the inside. The hearing aid guys use a 2cc coupler, which is definitely smaller. But for the 4cc, which is most popular in the consumer space, we have this bad boy. And so it's a 3D printed part. And what we have is a test coupon. We have a little pour-on material, compressible foam, and that seals into this cavity and allows the test coupon to be placed in and screwed down. So this test coupon uses the same MMCX connector that's on the earbud. So, basically take the earbud off and put the test coupon on, and then you can mount it into this adapter, which screws. Another foam surround is inside to make a seal against the 711 coupler without the collar on it. So just screw this bad boy in like this, and then reassemble with the test coupon in there. And let's put the foam in there so it makes a nice airtight seal. And then basically you have...
Just hold that up a little higher, Michael.
Sorry,
yeah, right
guys.
There. Okay, now we can see it. Perfect.
And then the test coupon goes in. And we put the cover on it, and you're able to measure this in the standard 711, which is good to 10 kilohertz.
Yep.
And you're off to the races.
Beautiful. What does the curve look like then?
I think I have some of that to show as well. Here you go. So here's a comparison to a full range BA. And so I kind of line things up for kind of output And we're pretty flat. We have a 2 dB LFRO from 20 hertz to 850, I guess. We kind of pick up a little bit there, you can see. And then you'll notice the behavior on the left of the Piezo MEMS is that it just increases its sensitivity as we get to our resonance. So what you don't see once we start climbing up in amplitude, we don't come back down until after our resonance, which is way high up in the spectrum. So if you look at a BA, it's always going to have that near 3 kilohertz kind of bump to make up for the ear canal resonance. So a lot of the BAs and dynamics or BAs from the hearing aid space, they're actually designed for, hearing aid resonances and things like that. So, there's always going to be those peaks, but they're also going to dip down and come up again and dip down and come up again and dip down. So you have to EQ with that. You have to work with maybe sometimes a couple of BAs to kind of smooth responses out. But with this type of transducer, it's a completely different response. And so now you have to think about how you're going to use cutting of EQ frequencies to shape your response, or using the passive damper, or actually tube geometries in the output tube of the earbud can be engineered so that they shape your output response. And just with mechanical engineering, you can wind up shaping the high frequency response to kind of look any way that you want, so any target curve that you're after. But inherently, the Piezo MEMS transducer becomes more efficient after 1K and continues to deliver amplitude into the system. Now, that's unlistenable. You don't want to hear that curve, but that's what it does by nature. And so that, in my opinion, gives you EQ cutting opportunities and not as much EQ boosting, which is probably much better.
I'm curious about something. You've got any insight into this, the BA receiver, and that would look probably similar to a dynamic driver too. When you measure it on a coupler, you see this sort of 3 to 4. There's the peaks. There's a couple of resonances, basically 3K, and then up again at 8K, whatever it is. But in the xMEMS plot, it seems to be gone. Is it just not visible, or do you have any insight into what happened to those peaks?
Yeah. Well, the B&K coupler, or just the 4cc volume in the metal tube, that has a resonance up near 12.5. Yeah. So those resonances are up there. In the coupler itself. What I think we're seeing here below 10 kilohertz is actually the behavior of the system. So that BA is behaving just like that. So the 711 coupler is pretty accurate below 10K. So it's not adding any influence on the frequency response below 10K. I shouldn't say any, but nothing that's going to influence the shape. That this BA driver was engineered to have that peak exactly where that is.
Okay.
Yeah, it's not a measurement artifact.
All right. So and typically you would have to put a low pass filter with the xMEMS. Or
the side fire lid actually attenuates frequencies above 10K. Okay. So this is the top port, but the side port will start rolling off somewhere around 8. Actually, so it has a different frequency response just by the lid design itself, and so don't have to tame as much of that free energy that you have in the upper octaves. Yeah. But what it does do is when I was listening to this initially, unprocessed, just raw, obviously it's, where's the bass or everything. But when I brought the volume down and I just was listening, I just wanted to listen. And I there's a lot of harmonics. So if you imagine a fundamental at 1K and you in the second and third and fourth and the harmonics that go out, this system's more efficient, right? So there's more amplitude there. And so I believe the harmonics was something that was really coming at me. So when you when people are going to tune these, they're actually leaving in a little bit more gain, not gain, they're leaving a little bit more of those highs in their products because it's revealing more detail of the recording. Because this is such a fast transducer and the transient response is so quick and it has such a well-controlled behavior that cymbals and decay of reverbs and high-frequency instruments like maracas and shakers and timbales and you get a busy mix with a lot of instruments that create sound energy above 5K and 8K and 10K, having a transducer that can accurately reproduce that and give some real energy, where you can see a lot of the traditional speakers that are in the market, they're falling off after 10K. Another popular company that's in the MEMS space with their driver, it rolling off after 15 and actually can't compete when you get up near 16, 18, 20 kilohertz. Now, there's not a lot of information recorded by instruments and singers in that range in the studio. However, there are harmonic artifacts in these instruments and in the room it was recorded in and things. And I think a lot of that comes through on this type of speaker than others. And then you talk about spatial audio and you talk about positioning things accurately in three-dimensional space. Since the phase is so tight and the drivers are nearly identical, the azimuth judgment error for a pair of these in earbuds versus a dynamic or a BA, I think the fastest dynamic we found was an in-ear monitor style dynamic, and it can resolve to 7 degrees azimuth judgment error, and we can resolve to 1 degree in 3D space. So basically, if you think about cues in a game or a film producer working with sound effects in Dolby Atmos or what have you, you can resolve the position more accurately with a fast transducer, especially a pair of them that are behaving the same. So it really gives you phase coherency, which equates into accurate delivery in 3D space.
Very interesting.
Yeah.
And the phase matching the consistency too, I guess.
Yeah, that is really important. Honestly, we mechanically have a derivation measurement from that laser system I mentioned earlier, and we were 2 degrees plus or minus 1 from 100 hertz out past 3. And we have companies that are experimenting with expanding the ANC bandwidth, getting past that 1-2 kilohertz, and they're actually getting 20-25 dB of cancellation, much higher up in the spectrum. I can't talk too much about it, but the algorithm engineers that are tuning ANCs are really pleased to have a transducer this fast. And by the way, a pair of them that will behave identically is really the game changing for them. So now we're working with microphone partners to get the fastest microphones we can in these circuits and let these algorithm engineers see exactly what they can achieve as far as performance enhancement and additional cancellation and wider bandwidth. And this slide here is just really kind of showing you that, no, the response doesn't have to look like that. We just want you to know, what does the transducer do by nature? How does it sound by design? How does the system behave? Once the engineers know that and get comfortable with the fact that we've got a different kind of impedance curve than you're used to seeing, we have a different frequency response than you're used to seeing, then they can start tuning accordingly. And so that's kind of why I like starting at the beginning, why is it, what's different? Transduction mechanism operates differently. We have a different material stack up. And of course, these unique attributes and behaviors need to be accommodated for when you go to test them. So that's why I think talking about testing them is really the best place to start, because that's where everyone in the industry is going to start. They're like, well, send me some samples. Let's evaluate your sand. Let's see what sand or hear what sand sounds like. and so, to help them out, we've got to do this kind of stuff that I'm showing you gentlemen today, make some EBK kits and come up with some adapters. And what you see here is on the right-hand side is a capture from Soundcheck. This is the stimulus window. So, we want to make sure people understand, how much millivolts RMS is required to drive the amp to get an equivalent output so you can understand what your results are. On the left is just a response curve for a DSP that was run to actually shape the EQ the way we wanted. So, just kind of went into the DSP tool and put a 5 bi-quad EQ in place. And we came up with something that would be close to what you would probably recognize already as the Harman curve or something close to that. So you can really shape whatever you want as far as a frequency response with this speaker. It takes EQ so well. I pump up the bass a lot, and I pump up the mid-range a lot, and I just kind of experiment with listening to the spectral kind of character of different bands of frequencies as I'm listening to different music. And at no time have I ever broken a speaker, and at no time has a speaker distorted. So pretty cool.
All right.
Yeah, and I think I've already showed you the impulse responses. I think the last thing was we wanted to try measuring a mesh, a protective mesh, in case someone wanted to cover the speaker and make sure that the mesh would, what would it do to the frequency response? So you can see a photograph at the bottom is kind of a metallic thin wire mesh with some pressure sensitive adhesive on there. So it's mounted on top of the test coupon. And I thought it was kind of cool just to kind of put this up here to show, we're experimenting with putting things over the lids because people are doing that. They're actually wanting wax guards in their products so earwax doesn't get inside or stuff doesn't fall in. So what would happen to the frequency response if we put a protective mesh on? Well, had to go figure it out. And you can see, a little bit of attenuation. It changes the response a little bit on the test coupon into the coupler. But not too much would it would prevent you from using it.
Okay.
Yeah.
It's actually one of my favorite durability tests in in-ear products is the Nutella test for earwax simulation.
Nutella, a flavorful test, I would imagine.
Yes, it's what's it called? Phonak told us that once, that they use Nutella to simulate the earwax. Anyways, just
wow.
Distraction to the conversation here.
That's funny.
All right.
Yeah, I think that's pretty much. That's the thank you slide. I ran out the content, guys. But my contact information is here. So if anyone wants to screen capture this and reach out to me, I'm on LinkedIn and my company email's there, and that's my cell phone. I'm not hard to find, and it'd be great to answer anybody's questions offline if they were interested in this.
And you guys also have office in Taipei or Taiwan, and anywhere else in the world?
We have. Let's see. I think those were the other. Let's see. Let me go here. So we have a facility in Taiwan, and that is where our engineering is conducted. We have distribution now set up, 2 distributors, and we've hired out country managers for the different territories. FAE, we just had our sales and FAE training, which was really exciting for us as a startup, getting into the point where, hey, we got customers beating on our door, we got to support. And so it's really fun time for us because we're bringing in, applications, we're bringing in systems, we're bringing in FAEs, sales directors. And so we're kind of growing pretty quick right now, especially after CES. We had a great reception there in our demos. We were actually surprised for the people that did show up, which it wasn't a highly attended show, but out of the people that did show up, I will say that at least 4 people had tears in their eyes listening to their favorite tracks. We had a listening station set up and just come on in and have a listen. And they'd put the earbuds in and ask them, of course, what would you like to have? And we would download it to the Amazon HD. We would download a 24-bit 96K uncompressed WAV file to the tablet and just said, here you go. And they were just, sometimes 15 minutes, they're just silent and just, can I hear another track? Yep, no problem. And one guy's crying. I mean, literally, he's like looking at the tissue that we're wiping stuff off with, and he's drying his cheeks. And he's like, that just the sound. Those are my favorite songs. I know this music, and I know the engineer that worked on this session, and I didn't know that was in there. This is great. So we're not semiconductor guys. We're not speaker guys. We make people cry. We're selling emotion, really. We're providing so much accuracy to the reproduction of the music that the intent of the musician, there's less in the way. Especially in the time domain with such a fast speaker. And so you can really hear stuff you've never heard before. If you guys, give me your addresses and I'll send you some demo earbuds and listen to Wish You Were Here from Pink Floyd on these things. You can hear people mumbling in the background. You can hear the guy, his chair squeak. You can hear, stuff that I didn't notice when I was listening on FM radio or vinyl at home with a nice setup. I thought it's, oh my God, the squeak in some of the Led Zeppelin songs of the kick drum pedal that, people say, oh, there it is. You can hear it through the whole track. but it's not like the highs are pumped. It's just resolving that high frequency content that's there. It's really something.
Yeah, I'd love to do that. There's one test that I think Richard Little told me years back was on Back in Black with very faintly at the beginning, Brian Johnson counts off 3, 4, and with a really good pair of headphones, you can usually hear the 4, but the 3 is hard to come by. And so right before Angus hits the guitar in that song is something always to make sure you have a well-balanced mid-range in your headphones. So that'd be an interesting track for me to try. But I think that's a whole discussion on what tracks and what little tidbits to listen to kind of, that's like a listening training course. Anyways.
Something, I'm glad you brought that up. Let me pull this up. I want to show this, guys, because I think it's important. You can't go buy a book or just have someone tell you how to tune these systems. You got to fail yourself into success. And pardon my bass rig screensaver there.
Yeah.
I'm looking for Amazon. Let's see. That's my reference rig there. 2.4 kilowatts, Mesa Boogie bass amps and Epiphany cabinets with the 5-string Spectre bass. That's my office away from my office.
Right.
So let me show you the playlist. So we have a playlist from Montera Tuning. And my playlist is now up to 14 hours and 35 minutes. And what we've done here is, since we've got staff in Taiwan and they're dealing with customers in Asia, they're sending me their reference tracks that their customers want to hear in Taiwan, in Japan, in South Korea. And so we're getting a lot of, hey, this is my favorite track. Hey, this artist, or this is what I use as a reference. So what I started asking our field application team and our sales guys is, please give me your customers' top 3 reference tracks. I want to know what people are listening to. So this is now, our list is up to 14 hours and 35 minutes. There's 163 songs. And guess who's listened to this thing several times through, from beginning to end, to make sure there's no sibilance and no artificial wacky sound in our EQ curve. You're looking at me. So over 450 hours of listening that I've done with these in my ears to kind of craft what I would say is, hey, try this frequency response. Everyone hears differently, and every company has a different target curve, or maybe they want to copy some other company's target curve. But be that what it is, you still, at the end of the day, have to put these in ears. Couplers, be damned. Metal tubes are not us. Even the ear sims, as great as they are still a representation of a standard system that we can at least have a Cal standard and a reference to work with. But at the end of the day, you've got the best mics in the world glued to your head. So let's use them. And so that's what I've been doing. And so there's music from the 50s, 60s, and 70s. I have some mono tracks, some old jazz stuff with one mic in a room where guys were just standing around, and when the sax solo came in, the sax player would just come a little closer to the mic and then back up later, all the way to modern recordings. So heavy metal, hip hop, Chinese music, instrumental acapellas, Hammond organ, church music, you name it. We have it all. So I'm going to ask you guys the same question. Please, along with your addresses, send me your 3 reference tracks. I want to know what they are. I want to add them to the reference list. I want to give them an audition, and I can't wait for you to hear the earbuds yourselves with your 3 favorite tracks.
Okay. Now, speaking of that, for anyone that's watching, is there any products in the market that they could go buy and try out your MEMS speakers?
Coming. Yeah. Well, at CES, we had several partners that brought over earbuds, hearing assisted device, TWS. I think there was a couple wired. So there was probably at least a dozen products in flow. We call them design wins and coming into production. Yeah, coming into production. So we're expecting
later this year, maybe September launch, something like this.
Definitely before Christmas.
Yeah. Okay.
And hopefully before summer. Really, I think spring release. Mercifully, I'm self-decoupled from the commercial side of the business. I'm a musician. I'm an audiophile. I'm into music. This is my happy place, and I'm pleased to not know how much it costs and who's doing what, and I'm just focusing on what I believe is a once in a lifetime opportunity to help audio engineers discover a new transduction mechanism and its benefits. And so that's where I've been focusing my time.
Okay, very good. I think that's a lot of information for today. So let's maybe table that for today. But we encourage everybody. We'll put Michael's contact information in the description below, and we encourage everybody to ask questions. Fire in your questions. I'll make sure that we get the feedback from Michael for you. So just please feel free to punch your questions into the below the description in the video here. And so yeah, anything else you'd like to add before we go, Michael?
I would say that most of the good stuff I can't talk about, guys. I'm sorry. There's, I believe we have at least 30 patents granted, probably more. Every week another plat comes in. And so there's patents coming in like crazy. And there's another probably close to 100 in process. There's a gigantic intellectual property estate. And being a startup and just coming out of stealth mode and jumping into production and being able to put out an amp, 3 speakers and one with a dynamic vent in the year and 4 months we've been kind of open for business is astonishing. But I wish I could really tell you what's going on, but without an NDA in place, I can only kind of cryptically describe and show some cartoons and stuff. But so if the questions come in are a little too specific, please cut me a little slack. An NDA may need to be put in place first before we can get into some real detail. So maybe that was some of the evasiveness that you heard from me earlier, Simon. I apologize. Yeah. I love the questions, but in a public forum, we have to be careful at the early stage because I think we got a tiger by the tail here. So we're trying to, do it the right way.
A lot of our viewers are pretty much heavy on the technical side, so I'm sure there might be some people reaching out and asking for that NDA and how they might be able to integrate these into some future products. So I guess let's wrap it up. Please encourage everybody to like, subscribe, and share, and all that good cheesy what do we call it? Social networking jargon. So I guess thank you, Michael. Thank you, Simon.
And hit the notification bell. Don't forget
one. Yes. I think only about 5% of our viewers are actually subscribed. So it's I think that's a typical trend. But anyways, I digress. I hope everybody enjoyed this episode, and we'll see you in a future episode. Thank you.
Appreciate your time, guys. Thank you.
Bye.